let's start this webinar about how CFD simulations can be used to boost the efficiency of processing systems. So let's start by a first presentation of the webinar and the agenda. So thank you all for signing up, and we are 67 participants who have signed up, and I can see that right now we are 41 participants in the session. So I think we can start. So you are all very welcome to introduce yourself using the chat box, and also please feel free to ask any questions that you might have, and together with my colleague Emil, we will go through all of the questions at the end of the session. Please turn off your microphone so we avoid any disturbing noise. I'm going to start by briefly introducing myself. My name is Miguel, and I'm a project manager and CFD engineer at Force Technology. And I work with CFD simulations, especially in the food and pharma sectors, and energy sector, maritime, and ventilation. And here you can see the agenda for today. After this brief presentation, I will do a short introduction to what computational fluid dynamics is, for those of you who are not very familiar with this simulation tool. And then we will discuss about why it's a good idea to use CFD in the design of processing systems, especially in the food industry. Then we will talk about how to apply CFD efficiently, and later we'll show some applications which can benefit from the use of CFD. And at the end of the session, we will have some time for questions and answers. So let's start from the beginning. What is CFD? CFD stands for computational fluid dynamics, and it's a branch of fluid mechanics which uses mathematical models and numerical methods to calculate and solve and analyze the fluid flows, such as gases and liquids. And as its name indicates, the equations are solved numerically by computers, instead of doing it analytically by hand. However, I think it's better to understand it with an easy example. In this case, we have a piping complex, or more or less complex piping system, where we want, for instance, analyze this part of the piping system. This is just a straight pipe. And when talking about CFD, that's what we call the fluid domain, and it's our control volume. This is the volume where we want to know everything about the flow, such as the flow velocity or temperature or pressure inside this volume here. And the first thing we do when doing a CFD model is we generate a 3D CAD model where we represent our physical system here. Then we define the boundaries of the fluid domain. In this case, we have an inlet here and an outlet, and then we have a wall. And the inlet it's representing where the fluid flow gets into the domain, while the outlet is where the flow gets out of the domain. And the wall is just modeling the inner wall of our physical pipe. And once the boundary conditions are defined, then the fluid domain is discretized into a certain amount of cells, and this is what we call the mesh. And there are different types of volume cells that we can use, such as tetrahedral or hexahedral or polyhedral cells. And the mesh, it's important to understand that the mesh can be discretized by more or less cells, and this is going to be one of the main factors defining the accuracy of the CFD model. And then once we have a mesh, we define the physics, and the physics are the equations. For instance, the equation describing the fluid motion, and this is what we call the Navier-Stokes equations. And then we can also introduce any other relevant physics that we might be interested in, or that might be relevant, such as two-phase flow or phase changing or radiation and so on. And at this stage, we also define the boundary conditions, such as the velocity and temperature at the inlet of the domain, and maybe the pressure at the outlet, and then also the boundary conditions of the walls. In this case, we can set it as an adiabatic wall, but we can also model the heat transfer through the wall if we think that it's relevant. And after setting the physics and boundary conditions, we run the simulation, and this is where the equations are solved numerically on each cell of the domain. And this is why it is important to understand that the mesh is going to have a big influence on the time that on the simulation time, actually. If we have a higher number of cells, then it will take much more time to run a simulation, as well as the complexity of the physics that we introduce to the model will have an influence on the simulation time. And this simulation time can take from seconds to several weeks, depending on the complexity of the model. And the last step here is the analysis of the results that we have obtained. And here is where we can see some interesting values on velocity or temperature or anything we consider is relevant for us. And all this can be divided into three major steps. The first one is the pre-processing, and this is everything we do before running the simulation. So it's where we set our CFD model. Then we have the processing part, which is where the equations are solved, and finally we have the post-processing, and this is the analysis of the results. So now that we have a general idea of what CFD is, I think it's also a good idea. Let's talk about why it's a good idea to use it in the design of processing systems. And let's take this example. This is a disinfection system for eggs, which is produced by Sonosteam, and if this physical prototype that we call here, that can be either an already existing system that we want to validate, but it can also be a concept of a product that we want to design. And for that, we can use CFD or simulations in general to make a virtual prototype of our physical prototype. And the big difference here is that while our physical prototype it's opaque in the sense that it's very difficult to know what it's really happening inside, and we can only measure, do some measurements by using some sensors in very localized points, such as the surface of the casing here, for instance, or the velocity at the inlet of the nozzles. So it's only giving very localized information, and only some variables can be measured depending on the sensors that we can use. And on the other hand, our virtual prototype, it's much more transparent. Well, it's actually 100 transparent, where we can see everything, absolutely everything related to the flow, in this case, inside the fluid domain. So we have access to information in the entire 3D space of our system, and also to all the relevant parameters of the case that we want to analyze. So our virtual prototype is giving us a much better understanding of our real system, or the physical prototype, or product that we want to design. And then if we think about the traditional design process of any product, we usually start by the concept of the product. Then we design a first version of the product, and after that we build a physical prototype, and we test it also physically by measuring with sensors and so on. And if the results of this test are found acceptable, then we will go to the production phase. However, in most of the cases, the design is not found acceptable at the first time, and we need to redesign and go back to the design phase and start the loop again, and do a new physical prototype and test it. And this can take several times until we get an acceptable results from this test, so we can proceed to the production part. And the simulation-driven design, it's a very, as you can see, it's a very similar approach, with a large difference, which is that we are using simulations from the design phase, and we are building a virtual prototype with our simulation tools, in this case with our CFD software. And then we are testing that by running the CFD model. And then, as in the case of traditional design, maybe the first iteration is not found acceptable, and we need to go back to design and start the loop again. However, while this is a very expensive and time-consuming process, when we do simulation-driven design, it is much cheaper and faster, since we are not building anything physically, and we don't need to spend the time and resources on materials and on testing. And at the end of the day, this is going to have a huge influence on cost and time. And just to give some business references in this article here from Carberg et al., which is available for free online, there are, I think, around 79 references, both from researchers and commercial companies. And just to quote a couple of them, For instance, already in 1996, Ortec Corporation claimed that they had seen up to a 75% reduction in development time and less costly prototypes. And then a few years later, ANSYS stated that a simulation-driven design approach leads to fewer but better hardware prototypes that serve to verify the refined design at greater levels of sophistication. And this can result in significant time reductions, cost savings, quality improvements, and product design innovation. And this is just two examples, but there is many others out there. So we can also use this comparison between traditional design and simulation-driven design to explain how to apply simulations in general and CFD in particular efficiently. And this graph here is a typical graph describing the costs of the design process of any product, and where we have here our steps from the previous slides: concept, design, prototype, test, and production. And all this is related to the time that of the design process. And we can easily see how the ability to impact the cost of the design is much higher at the early stages of the design process, while the cost of doing changes on the design increases dramatically over time. So if we now take a look to the effort that we usually put on traditional design, we can see that it's more or less spread over time, but it reaches a peak around the design and prototype phase. And on the other hand, when we do simulation-driven design, the high volume of effort, it's in this area here, and the concept and design steps, and this is where we have the highest ability to impact cost while having the lowest cost of design changes. So it is actually here where we want to put most of the effort, and that's what we are doing with simulation-driven design. Then if we think about the work, the CFD work itself, to me there is two key parameters to use CFD in an efficient way, and they are know-how and technology. And by technology, I'm talking about the state of the art of CFD, for instance, or about the CFD software, and about the computational power to run the simulations, and also about the graphic cards to get some nice and fancy CFD plots. So all this, it's something relatively easy to get. I don't want to talk that much about this, but I would like to focus on the know-how part, which is about the knowledge about CFD and the knowledge on fluid mechanics, and also the knowledge about the system that we want to design and analyze using CFD. And to explain this in a more detailed way, I have prepared some questions we should address ourselves before starting any CFD model. And first question is, which parts of the real system can be simplified? This will allow us to understand the 3D geometry of the model, or the 3D model that we are going to use for CFD. And if again we take a a physical system, which, as I said before, it can be an already existing system or a concept. In this case here, we are again looking at some nozzles from the disinfection system that I showed you earlier. And these nozzles are injecting both steam and ultrasounds for disinfection of food. And the first thing we do is we usually make a representation of the reality through a 3D CAD model. And this representation is trying to replicate the geometrical reality as much as possible. And then it can be used for construction or installation or any other relevant purpose. However, when we are building our CFD model, we need to think about if we really need to include all these details or if they are going to have any effect on the final solution, or if we can just simplify it and make a simplified version of these nozzles, for instance. So the key aspect here is to think about if we can simplify the geometry without paying a big cost on accuracy of the results. So what we can simplify without compromising the results. And in this case, the nozzles are a relatively small part of the entire system that we are analyzing. So they can be modeled just as straight pipes and with a round surface here, which is modeling the spray angle of the nozzles. So you might think that this is a small simplification, like it's not going to give us it's not going to be that much important, but when we have 20 or 30 of these nozzles in one system, it can actually lead to large savings in time when meshing the geometry, and since we are avoiding all these chamfers and changing diameters and all these details. And then after that, we need to ask ourselves, where are the areas of interest and where do the high gradients occur? And then we will be able to understand the mesh. And if we take again a SonoSteam example, this is a disinfection of chickens, where the chickens are moving from here, from the left to the right, and we are introducing steam and ultrasounds here in this area. And here we have the entire fluid domain that we have used for the CFD model. And as you can see in the video, on the sides here and here, the temperature is not changing that much. It's just a blue color all the time, and that corresponds to all this volume here and all this volume here. So it's a large part of the model, and actually all the high gradients and all the change in the temperature and velocity are happening here. So in the disinfection chamber, in this part. So yeah, of course, you may think that in this case it's obvious once we have run the CFD simulation, and we can see the results that here is nothing is happening. However, it's also relatively easy to force you if you have the experience and you know that, for instance, we are introducing all the flow through here and it's been sucked out from here. So we more or less know that is going to happen in this area. And if we now look at the same picture, but this time we are showing the volume size of each cells of the mesh, and where the red cells here are the biggest cells, and the blue color is the smallest cells. So we can see that the smallest cells are located both in around the disinfection chamber here and around the chickens, which are our area of interest. And all the rest here and here and here and here, it's everything with a higher cell size. And if we take again a closer look to the disinfection chamber, and we change a little bit the scale, we can see even better how the smallest cells are around the chicken surface and around the nozzles here where the high gradients occur, and all this part here is kept with a higher volume cell size. So the chicken skin is our area of interest, and this is where we want to refine our mesh so we can get more accurate results. And yeah, if you are not very familiar with CFD, then you can also think that yeah, but then I can just refine all the entire volume as much as I can, and then I avoid the problem of the accuracy. But then that would be extremely time consuming to run a CFD simulation. So again, the key is a compromise between cell size or the accuracy and of the results and simulation time. And last thing we should think about is these two questions: what are the input conditions and what assumptions can be made? And then that will allow us to understand the physics. And there is countless physics models that we can include in a CFD simulation, and countless of assumptions that we can consider, such as can I assume an adiabatic wall, or do I need to consider the heat transfer through the walls, or do I really need to consider compressible flow, or can it just be assumed as an incompressible flow, or can it be an isothermal flow, or can I use constant density, or does it need to be ideal gas, and so on. And here I just have I put only some examples of physics and boundary conditions that we can include in a CFD model, but there is many others, and of course, again, that will depend on the complexity of our simulation or of our physical system, and also it will depend on what we want to get from the CFD results, from the CFD simulation. So it's again a compromise between accuracy and simulation time. And now I would like to talk about some applications where CFD can be helpful, especially in the food industry. And I will start explaining something about the hygienic design. And I don't know if you are familiar with the Zinner circle, but I can do a brief explanation. The sinner circle is just a model which describes the variables involved in a cleaning process, and where the temperature is the temperature of the detergent, the chemistry is the strength of the detergent, then there is the cleaning time, and finally we have the mechanical force applied to the soil, either by the detergent or by scrubbing manually. And in the case of CFD, we will focus on the force applied by the detergent and not the manual scrubbing. And this sketch here, we're showing a couple of examples of how the sinner circle looks like for the cleaning in place process of a couple of closed equipments. First, here to the left, we have a straight pipe with a fully developed flow inside, and we can see that all 4 parameters have the same weight. And yeah, and on the right hand side here, we have the straight pipe but with a dead end, and this is giving a poor exchange of cleaning in place in the dead end region. And since there is a poor exchange of cleaning in place fluid, the action of the both mechanics, chemistry, and temperature, it's reduced, and the time here takes the largest portion of the cake. And this means that we will need more time to get a cleaning efficiency similar to the one in this case here. So this is an easy example to understand why CFD can be beneficial on hygienic design, since a good design can save a lot of time of cleaning. And this is quite easy to foresee by using CFD. And for a cleaning in place case, the mechanics aspect here can be directly linked with the wall shear stress, which is just the pressure that the flow applies on the wall in the flow direction. And then if we consider again the previous example with the straight pipe and the dead end, here I'm showing you some results from a CFD simulation. We are showing the wall shear stress plot on all the walls of both cases. And we can very easily see how this part here, where the dead end is, has a much lower wall shear stress. And the worst thing is that it's not only affecting this area, but the dead end, it's also affecting the area downstream the pipe, all here. So all this will also be affected by the dead end, meaning that it will give a poor mechanical cleaning compared to the straight pipe, where we can see that in all this area the wall shear stress is more or less constant once the flow is developed. And this won't only give a poor mechanical cleaning, but it will also give, as I told you before, it will also give a poor temperature cleaning and poor chemistry cleaning, since there is a lower fluid exchange here than here. And finally, here I have some other examples where CFD can be applied. And first, I will show, simulation of mixing tanks, where we can calculate for instance, we can calculate the time required to mix a tracer in any substance until a certain level of mixing is reached, or until a certain temperature is reached, or similar processes. And we can also combine, in this case, we can also combine CFD with structural simulations, for instance, and that's what we call a fluid structure interaction, or FSI, to calculate the fluid forces on the impellers, for instance. So we can use CFD to optimize the tank while minimizing the energy consumption and forces on the impellers. And this can be used both for, of course, food industry, but also pharma or chemistry or any other relevant industries or sectors. And then, as I already explained before, CFD can also be used to optimize disinfection or sterilization processes, where usually temperature on the surface of the food plays a key role, since we need to reach a temperature sufficiently high to kill the microorganisms, but not too high so it doesn't affect the quality of the food. And that we can predict it with CFD. And finally, CFD can also be used in a large number of applications in the food sector, such as baking, for example, where we can model the heat transfer from the heating elements into the air inside the oven, and then to the food products. And we can also model the moisture which is transferred from the food to the hot air and then removed from the oven. And then we have refrigeration, where heat transfer can also be calculated and simulated with CFD, and CFD can be a helpful tool to optimize the design of chillers and freezers, for instance. Then we have drying, where the drying, it's well known that the drying efficiency, it's a function of the air and very dependent on the air velocity and the airflow, and it can be really difficult to measure it during operation of a real system, since we need to install several sensors in different locations and also in different flow directions. And also CFD can be helpful here for design of spray dryers, for instance, and for optimizing the nozzles of the spray dryers, or we can calculate the droplets velocity or temperature or residence time, or any other variable which might be relevant. Then pasteurization, where we can set a CFD model to predict the temperature distribution of the milk during thermal processing, for instance. Heat exchanger design, where we can use CFD to optimize a heat exchanger based on any relevant criteria, such as heat transfer or pressure drop. And finally, clean rooms, which it's also relevant for the pharma industry, and where in clean rooms that the flow has to meet very strict conditions and regulations, and compliance is key. And CFD can be a very helpful tool to predict and to optimize these clean rooms. Finally, I have last short slide about other CFD applications that we do at Forest Technology to help optimize systems in other areas, and not only food and pharma, but also energy, where we do optimization of flue gas cleaning systems, such as this here, DSOX, DDost, and DSOX. Then we also do combustion simulations, and then we also work on the maritime sector and ventilation simulations. And as I said before, we also do fluid structure interaction, such as this here, which is it's a beam being deflected by the action of the flow. So if you are interested in any of this, you can let us know by sending us an email, and we can try to organize another webinar on any of these topics. And yeah, this is all for this session. Now I think we have some time for still some 18 minutes for some questions, if you have any. And yeah, we'll try to answer all the questions now, but if you have more specific questions, or we don't have time to answer all the questions today, you can send me an email here at my email address, mmal@force.dk. And thank you very much for participating today. And also, these here are the upcoming webinars on this hygienic design series of webinar, the 22nd of this month. So next Wednesday, I think Annette will talk about cleaning and cleaning validation. It will be in Danish though. And on the 29th, Jan will talk about choice of materials, also in Danish. And on the 6th of May, Jens will talk about food contact materials in Danish as well. And if you have any other questions, please feel free to send me an email.